Hello, and welcome to this Muddiest Points video. This screencast will go over dislocations and plastic deformation of metals. Some of the muddiest points received from students in regards to dislocations and plastic deformation were: why do the ripples or dislocations occur in materials in the first place? What exactly is a screw dislocation? If a unit cell is most stiff about its closely packed direction, why does it deform about it? How is slip related to different crystal structures, and how does it affect deformation? And then ductility and plastic deformation was foggy. So a little bit about plastic deformation. Plastic deformation is permanent deformation. It means that the material won't ever bounce back or return to its original shape. Plastic deformation occurs as dislocations move along slip planes in metals. Plastic deformation happens all the time. A couple real-world examples are if you had a soda can and crushed it in your hand, you would never be able to get the soda can back to its original form, so it would be permanently or plastically deformed. Another example is if you took a metal spoon and put it into cold ice cream, and maybe when you pulled it out the spoon bent and eventually broke. This would be an example of plastic deformation that led to failure. Car accidents are another example where you would see a lot of permanent deformation. When the cars collide, the bodies of the car actually absorb a lot of energy, which leads to the permanent deformation and dents that you see during a car accident. In dissipating this energy, though, they actually help keep the passengers safe, so deformation does not have to be a bad thing. Dislocations form when materials solidify, so there are already dislocations present in all types of materials. The number of dislocations in a material can be controlled. Dislocations will form when stress is added to a material. Deformation occurs as dislocations move through a crystal lattice. There are two types of dislocations, the first being an edge dislocation. An edge dislocation happens when an extra half plane of atoms is moved through a crystal lattice and comes out on the other side. When a shear stress, here and here, is applied to a crystal lattice parallel to the slip plane and in a plane where slip is occurring, this extra half plane of atoms, shown here and here, actually gets moved through the crystal lattice. So you can see that it's here and here. So you can see the edge of the plane here and here is where the dislocation is, and this is where the edge dislocation gets its name. As the stress continues, here and here, the plane is moved all the way through the lattice and emerges on the other side. And this displaces the entire top half plane of atoms, moving that part of the crystal lattice over. A good model for understanding dislocation motion is the ripple in the rug model. This model uses the idea of a rug placed on the floor, which would represent two planes, one on top of another. So you'd have the blue plane here and then the green plane, which you can't see but is underneath this one. If you applied a force to the rug, a ripple would form, which you can see here, which displaces the left edge of the rug. The same thing would happen in a crystal lattice. The left edge of the crystal was displaced by the shifted half plane. As the force continues, the ripple continues to move through the rug. Eventually, the ripple emerges on the other side. In the end, the top plane is displaced by the same amount that the ripple displaced the top plane in the second picture. The same thing happens in a crystal lattice. As the dislocation moves through, it eventually emerges on the other side, displacing the top half plane of atoms by one atomic spacing in the crystal lattice. It takes a lot less energy to move a dislocation through the lattice than it would to shift an entire plane at once, in the same way that it would be easier to shift a rug by moving ripples through than to slide the rug across the floor as a whole. This is why materials deform through dislocation motion when stress is applied. So, if deformation occurs through dislocation motion, how can it be stopped or slowed down? Dislocations moving or gliding on different planes can run into each other and get tangled, as shown here. This impedes dislocation motion, so more stress would be required to activate motion of new dislocations to continue plastic deformation. Higher stress required for deformation means the material has higher strength. Because of this, increasing the number of dislocations can actually strengthen the metal, which is the idea behind cold working. So we've already discussed an edge dislocation, so now I'm going to discuss the next type of dislocation, which is a screw dislocation. With the screw dislocation, as stress is applied here and here, the front plane of atoms begins to shift. So you can see that here. The front plane of atoms is in blue, and it is shifted over in reference to the back plane here. So you can see the front plane here versus the back plane here. The bonds attaching the top half plane to the bottom half plane break and then reform. So you can see that the back here still has the original bonds here, but the front has shifted over, so the bonds have reformed here. As stress continues, here and here, a dislocation glides across the lattice and eventually shifts the entire half plane over. So you can see the dislocation line here, which emanates from this point where the dislocation is moving across the crystal lattice here. This type of dislocation is called a screw dislocation because the top is partially displaced here. So if you were to actually travel along this dislocation, it'd be like going down a spiral staircase or moving along the threads of a screw. So if you went one spacing right, one spacing down, one spacing left, and one spacing up, you'd expect to be back where you started, but instead it's actually off here, just like if you had moved along the threads of a screw. Doing one full revolution around the screw should put you back in your original place, but because of the threads, you actually end up lower than you started. The same thing happens with a screw dislocation. The dislocation will continue to glide across the lattice until the entire top half plane is shifted over, which you can see in this picture here and here. In the end, the top half plane of atoms is still shifted over just like it was with the edge dislocation. Because of that, the final pictures look the same as they did with the edge dislocation. This makes sense because both screw and edge dislocations are mechanisms for dislocation motion. Next, I'll be discussing slip planes. So in the schematics on the previous slides, the bonds were breaking along a line and then reforming in order to allow the dislocations to move. This is easier along closely packed directions because the atoms are bonded more strongly, which means they are closer together, so it is easier for bonds to break and then reform. Because of this, metals deform along their closest packed directions on their closest packed slip planes. So each of these closest packed directions on the specific slip plane would be a slip system. So this schematic here is of an FCC crystal, and this would have 3 slip systems, so this one, and this one, on this slip plane. Deformation would occur along a single slip system, so one direction, on these parallel slip planes. So you can see in this schematic here that the crystal is deforming along parallel slip planes along a single slip system. So next I'll talk about the slip systems for the FCC and BCC crystals, starting with the FCC crystal. The slip systems in a material depend on that material's crystal structure. So first I'm going to talk about slip systems in an FCC crystal. The FCC, or face-centered cubic, is the closest packed crystal with close packed planes in family 111. In this plane, the atoms touch along face diagonals, as you can see here, which is this edge here. This makes this one of the close packed directions, which would be in the 110 family. Slip would occur along these directions in the 111 family of planes, and each of these directions would be a slip system of the FCC crystal. On this schematic here, you can see the 3 slip systems of the 111 plane. So I'm going to do a quick review of Miller indices if you wanted to find these directions on the 111 plane. So to find this diagonal here, I would draw my new axis here. So we have x prime, y prime, and z prime. And then for this diagonal, you move one spacing in x to here. So we went 1. You don't end up moving in y, so that's going to be a 0. And then you go down 1 in z, which is -1. And then you can connect your starting and ending points to see that you do get this face diagonal here. So 1, 0, -1 becomes 1, 0, bar 1, which you can see is the same as this diagonal here. So for the next diagonal here, you can use the same axes here. And for this one, there is no movement along x, so that's going to be a 0. And then it goes 1 unit along y, so that's a 1. And then it goes down 1 in z, so that's a -1. And then again, you connect your starting and your ending points. And then this 0, 1, -1 becomes a 0, 1, bar 1, which you can see is this diagonal here. So for this last diagonal here, you have to move the axes because it does not go through this axis here. So I moved my new axes to here. So I have x prime, y prime, and z prime. And then for this diagonal, it moved 1 in x, so that's a 1, -1 in y, so -1, and then did not move in z, so that's going to be a 0. And then you connect your starting and ending points to see that you did get this diagonal here. And 1, -1, 0 becomes 1, bar 1, 0, which again is this diagonal here. So you can see that with all 3 of these diagonals, you end up getting a +1, a bar 1 or a -1, and a 0. So that's a quick review on how to find Miller indices to find the close-packed directions in the close-packed planes, which would be the slip systems of your crystal. So we've shown the 3 slip systems for the 1, 1, 1 plane here. Next we'll look at the slip systems of the 3 other planes in the 1, 1, 1 family. Here are the other 3 close-packed planes and their close-packed directions for an FCC crystal. Slip would occur along each of these directions or systems. You can see that each of the close-packed planes are in the family 1, 1, 1, and each of the close-packed directions are face diagonals in the family 1, 1, 0. So total, the FCC crystal has 4 slip planes, these 3 here, and then the one on the previous slide, and each of these has 3 close-packed directions. Each of these directions in this plane would be a slip system, which means that there are 3 slip systems per plane. So 3, 6, 9, and then the 3 from the previous page means that there are 12 slip systems total for the FCC crystal. All these slip systems mean that materials with an FCC crystal structure tend to be more ductile. Next I'm going to talk about slip systems in a body-centered cubic or BCC crystal structure. So unlike an FCC structure, BCC crystals do not have a close-packed plane, but they do still deform along close-packed directions. The close-packed directions lie along body diagonals, which you can see here. The atoms are still touching even though the plane itself is not close-packed. Close-packed directions are group 1, 1, 1, which are body diagonals here, and slip can occur along families of planes 1, 1, 0, which is this one here, 1, 1, 2, and 1, 2, 3. So again, a quick review of Miller indices to find this body diagonal. I would set the new axes here have x prime, y prime, and z prime. To find this diagonal here, I would go -1 in x, 1 in y, and 1 in z, and connect the dots. So we went -1, 1, and 1, which becomes bar 1, 1, and 1. And then you could do the same thing for the other body diagonal. Next, we'll look at an example of each of the 3 families of planes on which slip can occur in a BCC crystal. Here are examples of the different slip planes for the BCC crystal. Unlike in an FCC crystal, slip can occur in multiple planes, so there are a lot of slip systems for BCC. Because there are no close-packed planes, though, it is harder for dislocations to move, so a greater stress is needed to cause deformation. Because of this, BCC crystals tend to be less ductile. You can see that although these planes look different, each of them does have at least one body diagonal. So the 110 plane and that family of planes will have 2 body diagonals here. The 112 plane has a body diagonal here, and the 123 plane has a body diagonal here. Now I'm going to talk a bit more about a term that I've mentioned quite a bit, which is deformation. This is a stress-strain curve, and if you aren't familiar with one of these, there is a Muddiest points video analyzing stress-strain curves. So the stress-strain curve has 2 different regions, the elastic region here and the plastic region here. In the elastic region, the sample will recover its original shape, so it will bounce back and it won't be permanently deformed. Once the sample reaches the yield point here, it enters the plastic region and begins to undergo plastic deformation. In the plastic region, the sample starts to become permanently deformed, but when unloaded, when the stress is taken away, the sample will still recover its elastic strain. This means that if you were to remove the stress, the sample would recover some. If you wanted to see how much a sample would recover after a certain point on the curve, you could draw a line, trace down from that point of the curve parallel to the elastic region. So then this would be the plastic deformation for this point on the curve. So here's the elastic recovery for a number of points on the curve, including this point here, which is failure. So the plastic deformation at failure is this here, and if you multiply this value by 100, you will get the percent elongation or the ductility of the sample. One example showing the different stages of deformation is a tensile test. For a tensile test, stress is applied in these directions, and the sample begins to stretch. In the elastic region, the sample stretches but returns to its original shape if stress is removed. Once the sample reaches this point here, which is the yield point, the sample begins to permanently deform. At this point, plastic deformation begins. Initially, there is uniform plastic deformation, which means that there is a uniform reduction of area. Once the sample is under the maximum amount of stress that it can take, at this point here, you can find its tensile strength. After this point here, the sample begins to undergo necking, which you can see here and here. Necking is a localized reduction of cross-sectional area, which means that the area of this part here is being reduced, while the rest of the sample remains constant. The necking continues to reduce the cross-sectional area until it reaches this point here, which is its breaking strength, and where you get fracture, and the sample fails. Stress-strain curves can also be used to compare the properties of different metals. Some of the properties you can look at are yield strength, tensile strength, breaking strength, percent elongation, and toughness. So first, the yield strength. I've mentioned yield strength before. This is the point on the curve where you switch from the elastic to the plastic region, which means you begin to get permanent deformation. So for example, that would be like here on this curve. You can see that the yield strength differs for each of these materials. The deformed stainless steel sheet has the highest yield strength, while magnesium has the lowest yield strength, way down here. A material's yield strength depends on a number of different factors. The next feature you can read from a stress strain curve is the tensile strength. Tensile stress is the maximum amount of stress a sample can withstand. This can be seen here at the highest point on the curve. Once again, the deformed stainless steel sheet has the highest tensile strength, and magnesium has the lowest strength. The breaking strength is the point at which the sample actually fractures. In this case, stainless steel actually has the highest breaking strength, even though it didn't have as high of a tensile strength or a yield strength as deformed stainless steel. The next property you can find on a stress strain curve is percent elongation. The percent elongation is the amount that the sample plastically deforms before breaking. This can be seen by the length of the curve. So again, to find the percent elongation, you would go out to this point here, where you found the breaking strength, and draw a line parallel to the elastic modulus. And then this value here, multiplied by 100, would be the percent elongation. So you can see that the annealed nickel alloy sheet had the largest percent elongation, which makes it the more ductile metal. Normally, strength and ductility are inverse properties. The more ductile a metal, usually the weaker it is, and vice versa. A stronger metal is usually less ductile. You can see that with the deformed stainless steel here. This material is very strong, but it is less ductile. Its percent elongation is very low. The final property you can see from a stress strain curve is toughness. Toughness is the area underneath the curve. You can see I filled that in for each of the metals here. And the annealed nickel alloy sheet has the largest area underneath the curve, which means it has the highest toughness, followed pretty closely by stainless steel. The annealed nickel alloy sheet had a high toughness because it had both a high strength and a high percent elongation. So those are some of the properties of materials that you can read from a stress strain curve. Next, I'll review what we've covered in this screencast. So, in summary, both edge and screw dislocations occur when stress is applied to a metal. The motion of these dislocations causes permanent plastic deformation. Dislocations move along close packed directions on more closely packed slip planes. And more barriers to impede motion of dislocations will strengthen metals. So, hopefully dislocations and plastic deformation of metals is a bit more clear now. Just to review, the muddiest points that we've answered today are: why do the ripples or dislocations occur in metals in the first place? What exactly is a screw dislocation? If a unit cell is most stiff about its closely packed direction, why does it deform about it? How is slip related to the different crystal structures, and how does it affect deformation? And then ductility and plastic deformation was foggy. So thank you for tuning into this screencast on dislocation and plastic deformation of metals.